to the inaugural, and possibly last depending upon how this video performs, episode of Microsoft Paint Evolutionary Biology. Here, I intend to use the incredible rendering power of Microsoft Paint to explain some of the most interesting and unusual concepts in evolutionary biology. No, 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 wait. It's more interesting than it sounds, I promise. Here, I know. Here's a simple and fun question for you. What is a species? That might seem like an easy one, right? Oh, whatever, you saw the thumbnail, you know it won't be. But if you had to try to define a species, what would you say? And people who actually know the technical answer, pipe down, I'm doing a bit here. Anyway, if something looks different enough, is it a different species? What about if they have a different survival strategy? Or live in different parts of the world? Have different animal pieces in those puzzles intended for toddlers under 3? Oh, okay, this feels like it should be easier, right? You know a different species when you see it. You're not out there confusing elephants and elephant seals. Although, never mind. Maybe if we start broad and hone our way down, the answer will become more apparent. You know that significant morphological differences between organisms exclude them from being the same species. A lion and an octopus are not going to be considered the same species even by the most wildly loose definition. You're not going to see the love child of Simba and Hank flopping around on the shore. Although they are both Disney. Anyway, moving on. How about something more similar, like African and Asian elephants? I mean, they're both elephants, but they're pretty different, right? Asian elephants are smaller, they don't have the enormous floppy ears for heat exchange in the savanna heat, and they live really, really far away from African elephants. I think most people would intuit that these two are different species as well. Although, there was one case of hybridization in captivity in 1979. This meeting resulted in a calf named Madi, who had some of the features of both species, but died after only a few days due to infection. Due to this, we'll never know if he would have grown up to be reproductively viable or been incapable of reproducing like most ligers. So far, pretty easy, right? If two groups are different enough physically, we can slap a different species label on them, even if they can potentially have offspring. But, I have a question. How many species of gorillas are in the world? Were you thinking one? It's actually 4, as long as you include the subspecies. And they look like this: the mountain gorilla, the eastern lowlands gorilla, the cross river gorilla, and the western lowland gorilla. They they look pretty similar, right? I mean, if you had to pick one out of a lineup, could you tell the difference? I don't think I could. And I do this professional. Well, I guess you have to learn. Whatever. The point is, they're hard to tell apart. More than that, there's significant evidence that they can and do interbreed when individuals migrate from the West. In addition, these offspring are viable and can reproduce, which makes sense, since there was significant interbreeding between the East and West groups up until about 80,000 years ago. So, what makes them a different species at this point? They look mostly the same, they can produce viable hybrid young together. I mean, aren't they just the same species at this point? Well, let's take a look at each population's range. Ah, there we go. These groups do not come in contact very often. In fact, there are easily detected genetic differences between these groups. So that may be the key to settling this question. There are actually many ways to define a species. Some definitions, such as the biological definition, are more descriptive, describing species as they actually exist and reproduce in nature. Others, such as the phylogenetic definition, are more functional and define species by the processes by which they come to exist. However, a far more general definition, and one that works better for our purposes, is thus. A species is a population of organisms that can reproduce and give rise to viable young, and, this part is important, do so habitually. The occasional road trip hookup with one of those lowland harlots does not a species make. Instead, you must be fully immersed in that local gene pool, and that pool needs to be distinct from neighboring ones. Sure, a little rough splashing might get some water from one pool into another, but as long as you can test the water from either pool and see a significant difference between them, it counts. Is this is this metaphor making any sense? The point is, there needs to be a distinct line where two different groups rarely cross. Romeo and Goriot must be the exception, not the rule. Of course, this definition has limitations. Individuals from species that reproduce asexually can't produce viable offspring with anyone other than themselves. By this definition, each individual is kind of a species unto itself, but of course we don't classify it that way. In these cases, a more functional definition of species is more applicable. Another area where various definitions of species struggle is in categorizing extinct species. We obviously can't observe the mating behavior of fossils, and in many cases for species that have been extinct for more than a few thousand years, no viable DNA exists for a more genetic approach. Look, we can't just rub bones together and see if the sparks fly. But other than those situations, our definition holds up pretty well, and it's the one you're most likely to hear in an intro-level biology course. However, we do run into another problem, and that is where a species exists as a smooth gradient. Imagine a river running through a valley. The bank of this hypothetical tranquil river is a little monstrosity that will expand our definition of a species. Behold, a tiny river salamander. Many hundreds of thousands of years ago, this little abomination moved in and established a population at the head of the river. They were successful, and slowly expanded down the course of the river over several thousand years, until their range covered the entire bank all the way down the valley. But that's a long distance, and the environment changes several times down the length of the river. These little guys were subjected to different selective pressures that resulted in substantial genetic differences between those living further apart. While those living at the head and the mouth of the river might not be able to reproduce anymore if they were introduced to each other, there is an unbroken gradient of reproductive viability down the length of the river. All those neighboring salamanders can make viable offspring, and hypothetically, a gene could flow all the way down the length of the river from generation to generation, even if individuals at the end wouldn't be able to pass it to each other directly. This does seriously test our definition. At a population level, it's a group of organisms that habitually reproduce and make viable offspring, but not all members of the group can reproduce? Where does that leave us? If you were to walk down the length of the river, you would never encounter a place where the population stopped and became a new one. We would have no choice but to consider this one reproductive population. So, so that's it. That's the end of the video. Even with a few complications here and there, our definition remains pretty strong. Even with a gradient like this existing, none of the rules we laid out have been violated. It's not like a situation like this can exist in anything other than a linear configuration. Nothing's blocking gene flow. Everything's fine. It's not like any of the members are separated by a clear line of delineation. No, come on. That's not fair. No. So, this is a ring species. It is an actual phenomenon that occurs in nature, and it utterly destroys our definition of a species. These little genetic cul-de-sacs occur when a species expands its range around some type of geographic obstacle, such as a lake in our little hypothetical scenario here. As a species continues to expand around the obstacle, they genetically diversify, becoming distinct from the original source population. Just like in our river gradient from earlier, however, neighbors can reproduce, and there's no clear line delineating the population until they meet back up at the far side of whatever obstacle is blocking them. This is where the complication occurs. Since the population exists as one smooth gradient, genes could hypothetically flow from one edge of the circle to the other. With neighbors habitually mating, it's one species, right? But here we have members of the same species existing in the same physical space, not mating, and not creating offspring. Is this one species? Two? One and a half? Okay. Let's work this out. If A can mate with B, meaning they are the same species, and B can mate with C, again meaning they are the same species, then, by the transit property, A and C are the same species, right? Following that logic around the ring, A and G are the same species, because of an unbroken chain of mating. But it's also not the same species because they cannot mate with each other in a natural setting. Okay, this isn't working. Let's look at some real world examples and see if that helps. The strength of the argument for some of these animals being true ring species vary. But this is a pretty cool one. A group of Laris gulls that colonized the area around the North Pole without actually crossing over it. By the time they circumnavigated the Arctic Circle and met back up in Europe, they had diversified too much to interbreed, even though all neighboring populations still could. Although there is the debate on how much they truly constitute an actual ring species. Next up, we have these great tits. A little bird with a range spanning from Europe to East Asia. However, we're primarily concerned with this area around the Himalayas, where once again, see animals colonizing around an obstacle only to meet back up on the other side and not be very compatible anymore. Although, in this case, it is hotly debated just how great these tits are. I mean, how great of an example of a ring species the great tit truly is. Anyway, next up we have my absolute favorite example, the trumpet fish. This fish's range spans the entire world and may represent the largest ring that a ring species has ever formed. However, just with our other examples, some of the evidence for being a true ring species is lacking. But I mean, who cares? Look at this thing. It's perfect. Alright. That was a lot of almosts and maybes. There must be a stronger case for this to be an actual phenomenon, right? Well, look no further than Astinia aschaltes. Uh, they, they really went and put an SCH in front of another SCH. They are a lungless salamander on the western coast of North America that spans from British Columbia to Baja, Mexico. They are generally categorized as one species with several subspecies. However, that description is challenged by the clearly definable ring they form around California's Central Valley. The subspecies sort of blend into one another, and just as in our hypothetical, neighbors can breed with neighbors, and genes could potentially flow throughout the population without any hard barriers. Except right here. So you're telling me that Organogenesis is the same species as Aschaltes and Crocreator, but Aschaltes and Crocreator can't swipe right on each other? This relationship status is so messy that these salamanders form what is called a species complex, a population of closely related organisms with such similar features and that can interbreed so readily that the boundaries between them is often unclear. This didn't really help us, did it? Are they one species or two? What even is a species at this point? Well, maybe being able to draw hard lines in the sand isn't actually all that important. Biology is messy, and hard lines very rarely form in nature. As Kutcha and Wake suggest in their 2016 paper published in Ichthyology and Herpetology, a ring species allows us to see the gradual and ambiguous process of speciation, the formation of new species, occurring over geographical distance rather than temporal distance. This really isn't that much different from a population of one species becoming a new one over millions of years. Think about it this way. You're the same species as everyone around you, and as the people of the previous generation, and the one before that, going back nearly a quarter million years. There is no one generation where you can draw a line and say that on one side are modern humans and the other side is not. Still, if you go far enough back, there would be no modern humans. It's a gradual process. To complicate matters further, the various species of human could and often did interbreed, and if any of these populations had merged back into one, they easily could have been one species again after a few thousand years of interbreeding. The fact that they remain distinguishable is why they're considered a different species. How confidently we can call organisms a different species is a gradient that tries to reflect a natural process that has no concern for our labels. For example, if you went far enough back, you wouldn't be able to have offspring with any hominid species present at that time, showing how the divide between species becomes more impenetrable over time, just like a ring species. We don't know exactly where that divide is for us, and I have no real interest in finding out. But maybe if you're feeling adventurous, you can make a contribution to science and
Take one for the team.